Howdy students, and welcome to the last video in chemistry. This is nuclear chemistry part 3, and in this video we're going to look at a couple extra things that pick up from the last video, and then we're going to look at a little bit of history of nuclear radiation and how nuclear chemistry really affects our daily lives. So the first thing we're going to do is talk about transuranium elements. Transuranium elements are elements that are above the element uranium, which is atomic number 92. These don't really occur in nature, so if you look at a periodic table, you will start to enter what we call the synthetic elements, or the ones that are created by uh, laboratories, particle accelerators. They're radioactive. They're made in particle accelerators and nuclear reactors, and we can create some of these different elements by using things called nuclear fusion, fission. We can split atoms, we can bombard things in order to create transuranium elements. So one of the ways that we can do that is with a particle accelerator. We call these atom smashers. We spin atoms around in a circle using magnets, get them up at extremely high speeds, and we can create different atoms. These are also known as supercolliders. Subatomic particles are accelerated by magnetic fields, traveling close to the speed of light, and they smash nuclei together. And what we can do is fuse in order to form something brand new. Texas A&M University has a small one called the cyclotron, which is in our physics building on University Drive. It's kind of like an atom racetrack, if you will. And you can take tours of the cyclotron. In fact, that's one of our topics in our nuclear research project is learning about the cyclotron here. Now, there's a large particle accelerator in the Fermi labs in Illinois. And you'll see these two large racetracks, essentially, where they will speed up these atoms, have them go around and around and around, and eventually we can create new transuranium elements. There are two types of nuclear reactions. We have fission, which is the splitting of a heavy nucleus into two nuclei with smaller mass numbers, so we can actually break it apart. So fission is all about breaking down, breaking apart. This is used for nuclear energy. So here's an example. If we have a neutron being added to uranium, then we can use fission and break this down, this uranium element, into two smaller atoms like barium and krypton, producing 3 neutrons here. And when this happens, when we have these 3 neutrons, those, just like this one started out, can cause what we call a chain reaction. So when we have one hit, 3 more neutrons are produced, and so on and so forth, and we get this exponential chain reaction. Now, if that's uncontrolled, we can have pretty severe consequences. But we have ways of controlling this. So for instance, 1 kilogram of uranium-235 is equivalent to about 20,000 tons of dynamite. So that's like a stapler weight being equivalent to 20,000 tons. So nuclear energy is very efficient, but it can be slightly dangerous. So here's a little image for you. This little tiny pellet of uranium weighs about 7 grams, and it can generate as much energy as 3.5 barrels of oil, 17,000 cubic feet of natural gas, or 1,700 pounds of coal. So a lot of people want to use nuclear because the waste is just so little. But we have this consequence of chain reactions that we'll learn about in just a little bit. So nuclear reactors, we can kind of get a good idea here with this diagram below. They're carefully controlled. Much of the energy is heat, and we use that heat to heat up water in order to power a turbine, which generates electricity. So a coolant is needed, and we usually use water. The water or carbon also acts as a moderator. It slows the neutrons down so they can be captured. A lot of times we call these types of control rods. So a lot of times the control rods are made of cadmium to absorb excess neutrons in order to slow down the reaction. They can be raised or lowered into the reactor core. So this little red box down here is where we actually react the uranium or whatever radioactive element we are going to go through fission. The control rods help slow the chain reaction. We can heat up the water. And these big towers that you see are actually the cooling towers. They cool down the water that's been heated up. So a lot of times this is what you see in real life. Now, Chernobyl, there was a disaster back on April 26th of 1986. A reactor at this plant in Chernobyl exploded. There was fire. Clouds of radioactive particles were released. And if you look at the image, you can see that the radius of the damage was pretty severe. The orange lines here were areas of severe damage. And then the radius was where they were finding radiation. There were 56 direct deaths at the plant, estimated that as many as 9,000 people among the approximately 6.6 million most highly exposed. And they may die from some form of cancer. Being exposed to radiation kind of messes with your cells in your body. So, tragic. Chernobyl. At the end of the year, we're going to try and show a documentary that looks at Chernobyl and just the implications of that explosion. Here's an image of Chernobyl. You have the reactor site, cooling towers, and just this massive, massive pit where the explosion hit and fire ensued. The area of Russia around Chernobyl experienced an increase in many health problems. Different types of cancers arise, thyroid cancers because of the breathing in of radioactive iodine. Tumors were increased due to the inhalation, the breathing in of radioactive dust. A lot of birth defects for women who were pregnant. Malformations increase in people who were young adults at the time. So just really, really sad, honestly. A lot of people were affected by this. So nowadays, you can see that current nuclear reactor sites are built with a 4 feet, that's 4 feet, thick concrete barrier wall. It's a containment building. So literally they surround the plant with a dome of concrete. Now, you'll notice that in the Russian Chernobyl one, they had a 2-foot concrete wall that went right and stopped above the reactor. So there's really no way of containing this area here. And so nowadays we have basically learned from the mistakes of this tragic incident. So the second type of nuclear reaction is called fusion, which is the combining of two like nuclei to form a heavier, more stable nucleus. So we're actually combining things. So we're not breaking down, we're going to combine. Stars produce their energy this way. Stars will fuse atoms together to create larger nuclei. So we start with hydrogen generally and then go to helium and lithium and beryllium. Currently, high temperatures are necessary in order to initiate fusion. This is a possible future energy source and able to actually harness that energy. So here's an example. We have 4 hydrogen protons here plus 2 electrons. And what we can do is actually combine those two. And when we do that, thermodynamics actually has energy being released as a product, which is exothermic. So we can actually find ways to capture that heat. So here's an example. We might have an atom called deuterium, which is just a hydrogen proton with it's going to have a mass of 2. And then tritium, which is H with a mass of 3 and 1 proton. You can combine these two to form helium, 4 and 2, and then a neutron is released, and energy, which is what we're trying to capture. We form a larger element with fusion. Energy is still a product. So, being able to understand this concept, it was used to actually win World War II, which was pretty incredible. And so we're going to talk a little bit about that right now. Top secret. We were involved in World War II, and our government put together the Manhattan Project, which was a task force dedicated to developing a nuclear weapon. We were able to create an atomic bomb using the minds of all these men who were recruited into this Manhattan Project, and also women, a lot of influential women that were used to help with the calculations involved. So just incredible teamwork overall. But we produced an atomic bomb, a hydrogen bomb. Fission reactions caused a fusion reaction. So we used fission to create a fusion reaction, and it was a chain reaction. So we're going to talk a little bit about that as well. This is 1,000 times more powerful than fission bombs alone. So the first one we created, we actually did one test run, and this was the second bomb that was actually dropped on land, civilians. The first one worked, and they said, okay, let's go. This was called Little Boy, dropped on Hiroshima on August 6th of 1945. Basically, you have a uranium core on the inside, and when the bomb hits, targets the uranium and starts the chain reaction. So here's a little image that shows you the before and after. You see lots of houses, streets. In the after picture, can't really tell the streets. Looks like a lot of dust, a lot of clouds, a lot of buildings are gone. Pretty tremendous devastation. And the reason they bombed Hiroshima was because it was a military base for the Japanese. Fat Man was the second bomb dropped on August 9th of 1945. That was on Nagasaki. And this one had a plutonium core. And once again, we were able to create a chain reaction there. And you'll see again, the before and after shot. You've got buildings, streets, and then on the right, you've got dust. And looks like some of the main streets are still there. You can see the river, but gosh, a lot of the buildings were completely leveled. In Hiroshima, approximately 70,000 people were killed as a direct result, and a similar number were injured. So that'd be about 140,000 dead or injured. A great number more would later die as a result of fallout, the radioactive decay and the radiation, and cancer. Unborn babies died or were born with deformities. Clothing was burned into the skin. An estimated 40,000 people were killed outright by the bombing of Nagasaki, and about 25,000 were injured. Many thousands more would die later from related injuries. So again, the radiation, the sickness from the fallout was almost just as bad as the blast itself. So here you can see Nagasaki and Hiroshima both were military ports that were pretty significant in supplying the Japanese army with weapons and ammunition. Tokyo, of course, would have been tragic if we struck there, but it would have had no advantage to the war. So Nagasaki, here's some images showing the fallout. So the H-bomb that was used had that plutonium core, and a hydrogen bomb kind of is where you get this nuclear warhead shape. And this is called a fusion bomb here. Tremendous amount of energy, huge blast. You get this mushroom cloud effect going. A lot of people are familiar with this image. Now, disposal of this, disposal happens where we take the used up uranium, the nuclear waste, and we actually put it into little barrels. And currently we are storing it under the Yucca Mountains, which is out in Nevada. And right now, this is our best way of recycling nuclear waste. So you could find a way to recycle nuclear waste more efficiently, then you'd probably be a millionaire. A lot of times, if we do this, though, we have risk of getting nuclear radiation into our water systems, our biospheres. And so right now we're working on ways to prevent all of this. So after being buried for about 1,000 years, most of the radioactivity will be decayed. So right now our best thing is to bury it and wait 1,000 years until the radioactive decay is safe. So here are the Yucca Mountains. No one's around. Hardly anyone lives out here. They thought this is the safest place to put it. So right now that's where they go.